Okay, welcome back to the second part of this afternoon dedicated to Emmy Noether. We follow with we continue with the lecture, which is called Emmy Noether by Capi Corrales here of the Complutense. So please, Capi.
Thank you, Giovanni. First, thank you, Ilka. It was a great talk. When I prepared this talk, there were two things that I did not know. One was what you were going to say. So I'm going to rush through some of my slides quite quickly because I don't want to repeat what you said. So I won't talk at all about Emmy Noether's life or anything or situation. And second, I did not know which was the mathematical level of the audience. And as a couple of times Ilka has mentioned, Emmy Noether's work was very high-level mathematics. The smallest of her achievements, sorry, my English is rotten today. I'm not in an English mood today, so I'm going to talk very poorly. Anyway, the smallest of her achievement would require a large amount of explanation just to understand the definitions. And it makes no sense to give here all that machinery. I was thinking of which one would be a statement that every student that has gone through mathematics in Complutense would understand. And I have found one, which is, everybody set yourselves in algebraic equations, okay, Galois theory. So everybody knows that for an algebraic number to be constructible with ruler and compass, the degree of its minimal polynomial has to be a power of 2. So we can reach it through quadratic extensions. What about the converse? Is it true that if a number has as minimum polynomial an irreducible polynomial of degree a power of 2, it is constructible with ruler and compass? And the answer is no. There are a number of examples of degree 4 polynomial, none of whose roots can be constructed with ruler and compass. So the question is, which is the property that is an if and only if? And the property that is an if and only if is an algebraic number can be constructible with ruler and compass if and only if the degree of the Galois groups of its minimum polynomial is a power of 2. That's Emmy Noether's result, first published in van der Weyden's book, which was one of her students. So that's the simplest things I've been able to come about to, and that's all I would say solidly. So, wait a minute. So Emmy Noether, I want to talk about her mathematical ideas, and this is a quotation from André Weil. You know, a lot of mathematicians. Can I put this in a? Miguel Ángel, ¿me puedes poner esto en una pantalla grande? Porque no lo veo para traducir. Tengo dos pequeñitas. ¿Me puedes hacer una grande? Es que ahí está lejísimos y ahí me duele el cuello. ¿Me puedes poner una pantalla? Excuse me, I want only one screen because I don't need to see the next one. ¿Me la haces una sola pantalla aquí, sí, no dos? Vamos a ver, es que no me acuerdo. Es que no veo. Si es... No, vale, mal. See, I'm going to translate this from the original.
No, es que lo estamos viendo. Vamos a ver.
Ahí, ahora esa.
Sí, pero ¿cómo se hacía aquí para verla a tamaño completo? La verdad es que me...
Ok.
Pero vamos a ver, si quieres.
Opciones de cambiar. Ahí. ¿No está en cambiar? Vale. There you go. Muchísimas gracias. Okay. You know, a lot of mathematicians have only one idea, which is better than having none, after which they exploit it all their lives. Just think of Mittag-Leffler. On the contrary, Kovalevskaya had first the idea that took her independently of Cauchy, of what we call nowadays the Cauchy-Kovalevskaya theorem, and after 10 years, she had the idea that took her to the, ¿cómo se dice? Eh? Spinning top. Thank you, the spinning top of Kovalevskaya. Well, Emmy Noether had much more than two ideas, as we will see. So that's one of the several reasons for which she's an exceptional figure, as Ilka has said. What I'm going to be talking about, the works, I have taken them from Emmy Noether collected works. You have them in the library here. Well, right now it's on my desk, but I'm going to bring it back after this talk. And general descriptions of Noether's work, you have them in Alexandrov's and Neil Jacobson's papers. And also there was some wonderful conference in 1996 in Israel on her work and the proceedings of this conference have a lot of papers describing the different aspects of Emmy Noether's work. So, Emmy Noether, as Ilka has explained to us, worked mostly in around three mathematical communities, Erlangen, Göttingen, and Princeton, because yes, it's true that she was living and teaching in Bryn Mawr in United States, but she was going weekly to the seminars in Göttingen, in Princeton, to work with her colleague mathematicians. So she did research in Princeton, although she lived in Bryn Mawr, I will say it wrongly. So in these three mathematical communities, which were and are still three of the top leading mathematical communities in the world, and it is from centers like these three ones from which we get the guidelines to value the work of mathematicians all over the world. And it is valued on three legs, so to speak: the intrinsic value of the work of a mathematician, the influence that the work of whatever mathematicians we are studying has around doing research around the person, and the variety of the subjects that this person has approached. These are the three main aspects that are valued from the curriculum of any mathematician. So, the subjects in which Emmy Noether worked mostly were algebra, topology, and physics. So since we have 3 points of view and 3 subjects, I've matched them in pairs. I've done it. So I'm going to talk about the intrinsic value of algebra, the influence in topology, and the variety of subjects in physics. So what I did was, sorry, all this is, I'll put the quotes in the original language in which they were written. So what I did is I wrote email messages to my colleagues and asked them exactly in which subjects, exactly which results of Emmy Noether were teaching, because what happened with Emmy Noether, as well as happened with Alexandre Grothendieck, in my opinion, is that they are the 2 mathematicians of the 20th century whose work has influenced more the gaze, the glasses under which we look at mathematical objects in the 20th century. So it's hardly impossible to find any contemporary mathematician doing research that is not doing research a la Grothendieck or a la Noether. Because really, we do research not knowingly under their point of view, but never you say, this is Grothendieck, this is Noether, for 2 reasons. One is that most people don't know about it, and the other is that their research is so specialized in many ways because they didn't teach initial courses. They only worked with colleagues that were doing research as they did, that it's hard to put it into frame, except that now Emmy Noether's work and point of view is all over linear algebra, algebraic structures, commutative algebra, and algebraic equations in this faculty. So in my part, the isomorphism theorems in linear algebra and amplification of mathematics in computer science. It's very possible I use something else, but I'm not conscious. To say that the isomorphism theorems for vector spaces, groups, first isomorphism theory, second isomorphism theorem, third isomorphism theory for rings, for groups, for all of those are Emmy Noethers in all of the subjects that you had seen. In computative algebra, the normalization theorem by Noether, Noetherian rings and modules, given their name in their honor. If a ring has the condition of ascending chain of ideals, if of the ascending chain, their ideals are finitely generated, the Lasker-Noether theorem. In algebraic geometry, algebraic and analytic geometry, the first two, and directly the other two ones. Since this is going to be in internet, you can look for what are the statements of these theorems. I won't go into them. Mariemi, Pedro, Hanale just answered. Besides commutative algebra and linear algebra, Noether is everywhere in algebraic and structures and equations, which is true, as those who have taken the courses, at least with me, know. Algebra. So let's go to algebra, and here we have Jean Dieudonné from the group Bourbaki. Noether was then in the process of entirely reshaping algebra in what became known a few years later through van der Waarden's work as modern algebra, systematically giving preference to concepts over computations. Concerning in particular linear algebra, she was liberating it from the plague of matrices and determinants from which it had been suffering from a century, replacing these cumbersome and geometrically meaningless tools by the intrinsic ideals of modules and homomorphisms, which allowed, for example, for extensions of fields to be looked at as field vector spaces. And thou then was able to put all of Galois theory into the frame, the modern frame that nowadays we follow. Now, Emmy Noether was not teaching, and she was running seminars on these subjects to which van der Waarden and Emile Artin were attending. So a lot of her ideas, we can find them in van der Waarden and Emile Artin's books. Now, reading the letters and the comments of her colleagues and students, you can go back and identify which of those results are hers. But the framing, this is van der Waarden, Emile Artin, they were Noether's point of view. No? These two works in ideal theory were really the clue not only for commutative rings, but also to be able to look at fields extensions in such a way that allowed the contemporary framing of much of algebraic number theory or Galois theory, etc. And here we have it described by Bourbaki. If we set aside the works of Steinitz on fields, you mentioned Steinitz after. The first important works in the study of general commutative rings, which of course number fields have the rings of integers, like Z is the ring of integers of Q, are the two great memories by Emmy Noether on the theory of ideals. That of 1921 about primary decomposition. You know, a prime ideal is a generalization of a prime integer, and a primary ideal is a generalization of a power of a prime number. And Noether proved that if you have a ring that all of its ideals are finitely generated, then every ideal can be decomposed as a finite product of primary ideals. Eh? Intersection theorem. Gracias, I knew I was saying it wrong. I looked at the right person. With these memories by Emmy Noether, the long study of the decomposition of ideas started years earlier, years, it was a decade earlier, was concluded at the same time that cumulative algebra was born. Now, in topology, so you understand, classically a surface was studied with a triangulation. For example, Gauss at the beginning of the 19th century was the director of the astronomy center in, where was he? Around Hanover. I don't recall where the astronomical center was. So, okay. And he was asked to do a map study of the region of Hanover. So he did a triangulation with geodesic triangles, and from that he deduced a lot of his research on intrinsic geometry, curvature, following Euler's work, etc. Now, for a compact space, you can generalize this triangulation, and if you generalize it, I don't have here the year. Do I have the year? I don't have the year. Anyway, you generalize these geodesic triangles to simplices, and you do a triangulation, and that's what Poincaré did. Now, what did Poincaré is he was able to develop a system of integers, thanks to which he was able to find invariants that depended on the topology of the space and not on the concrete triangulation. So what Emmy Noether did, these invariants was the Betti numbers, in case you have studied them in your courses, and the torsion coefficients of the compact space. So she was able to translate all of this work of Poincaré, which was with matrices and determinants, to modules and homomorphisms that's giving way to cohomological algebra and the work that here Sanjurjo and Ruiz described. Hopf completed his habilitation in Göttingen between 1925 and 1926. The deep friendship that he developed there with Alexandrov lasted until Hopf's death. Their common interests in mathematics facilitated the introduction of Hopf in that world, and he's been accepted in the not easy to access circle of Hilbert, Courant, and Noether. Alexandrov explains in his autobiographies how during a dinner in Luitzen, in Brouwer's house in Blakirum, Holland, in December 1925, Noether explains to those gathered there her idea to substitute the Betti numbers in a complex for what she called Betti groups, defined as quotients of the group of cycles over the subgroups of the borders of the complex. This notion, that of what we know as homology groups, was crucial for the development of algebraic topology and was immediately adopted by Alexandrov, Hopf, and Vietoриus. In particular, Hopf showed how the Euler characteristic, understood in this new context, allows us to give a simple and elegant proof of the fixed point theorem of Lipset. So you know concretely, those who have the course, what we are not talking about, and those who don't have the courses, you keep thinking. And of course, all of her influence on topology, you can find it in Jean Dieudonné's article. It's only 2 pages, but it's really a summary of exactly where in algebraic topology you can trace all of her influence. And I don't think it makes much sense here to go deeply into this content, but to give you the information of those of you who have the knowledge where to go, because that's what you gave us to it. It makes no sense to be here pedantic. Now, physics. Oh, too small. Okay, I translate for you. So I did the same for physics. So we have here, I used several times a result of Emmy Noether in my research and also in teaching. The laws of conservation in dynamical variational problems when there are symmetries. It's an advanced topic that has appeared in the doctorate course, Fibers and Gauss theories. In mechanics, the laws of canonical conservations. Do you really want the translation? You know this. Okay, the first Noether theorem, the second Noether, I'm going to explain Noether's theorem. So Noether's theorem in physics is all over. So you just see Otto, you see all of your teachers are here. And that's the only theorem that I'm going to explain. So, okay, I'm going to explain this. So believe me, it's all over the courses here. Okay, so here we go, one of the top physicists in the United States. The connection between symmetries and the conservation laws is one of the great discoveries of 20th century physics. But I think that very few non-experts will have either heard of it or its maker, Emmy Noether, a great German mathematician. It is as essential to 20th century physics as the famous idea like the impossibility of exceeding the speed of light. It is not difficult to teach Noether's theorem, as it is called. There is a beautiful and intuitive idea behind it, which I'm going to give you following his Lee Smolins papers. I've explained it every time I've taught introductory physics, but no textbook at this level mentions it. And without it, one does not really understand why the world is such that riding a bicycle is safe. To tell you the way this theorem was born is that in 1915, Hilbert called a lot of people to Göttingen to attend the lectures that Einstein was given on his general and special theory of relativity. Now, there was a problem that Einstein could not solve, and that was the problem of preservation of energy in the general relativity theory. He could describe how preservation of energy worked in the special relativity theory, but not how it worked in the general relativity theory. So he wanted to explain to as large possible audience of mathematicians and physicists which was the concrete mathematical problem that he was hitting against not being able to solve, to see if someone gave him an idea of how to solve it. Emmy Noether solved this problem, and she kept doing research on this problem of the preservation or the conservation of energy, which led her years after to this theorem. And what she understood was that in both cases, in the general and in the special relativity theory works, what was an essential object that codified a lot of the information was what is called the group of symmetries. Depending on which group of symmetries, the conservation laws work one way or another. What happened is that in both cases, you have a Lie group. She understood it. But in the special case, in the special relativity theory case, the Lie group has a finite number of infinitesimal generators, while in the general relativity theory, the number of infinitesimal generators is infinite. And that's why the behavior was different. And this is what took her to this. So here is what are the bibliography that I have used for what I'm going to explain to you now. So you look at this. Now, you have a marble that you throw it in a paraboloid. If you throw it in just a vertical way without effect, it just goes up, down, up, down, up, down. But if you throw it with effect, At least we call it when I played marble as a little kid with effect. So it doesn't go through one of the directly vertical, but with effect. Just a minute. Here. I repeat it. How do I repeat it? Ay, sorry. Ah, there you go. You see how it goes? It moves, but there is something that keeps being constant. And what keeps being constant in this movement is the angular momentum, which is the product of the mass of the marble, the distance to the center, and the velocity with which it moves, it rotates along the center. So the reason is that this hyperboloid has a symmetrical shape. So what she discovered can be stated here. I translated it into English for you. Let me find a page. If a system has a continuous symmetry property, as it is here, the shape of the hyperboloid, then there are corresponding quantities whose values are conserved in time. And here is the angular momentum. So what you have to do is whenever you have some symmetry, you know where you have to put your focus. Search for the invariance in time, and that's going to give you a description of what you're working with. I think that all the rest, I was going to talk about her influence in what are known as the Noether boys and the Noether woman, but I think you have them here. All of the research of these men here are very influenced by her. In terms of the woman, we have Greta Hermann in Germany. She Noether directed her thesis, and then in Bryn Mawr, she taught all of these women. Olga Tosky taught. I had her as teacher of matrices in the United States. She was a top researcher and a great lady in number theory. Greta Hermann, of which Mariemi Alonso knows a lot. If you want anything to know about Greta Hermann, you ask Mariemi here in the first row. And she worked in 3 subjects. In mathematics, she wrote really a seminal piece of paper for computer mathematics, computational mathematics, the question of finitely many steps in polynomial ideal theory. This is the subject of her thesis under Emmy Noether, and see 1926 that it's really an advanced topic for the subject because it's a topic which is essential when you are doing computational mathematics, and it's 1926, way before there was any computational mathematics. She was awarded the prize in physics and philosophy from the Academy of Saxon for her works in the philosophy of physics. And then she was founder of one of the great schools of educational pedagogy in Bremen, of whose details you can also go and search for them because that's really documented in internet. So I'm just going to give you this is Olga Tosky. I had to put her photograph because she was my teacher. Okay, she was fabulous. And I want to very quickly talk about what I learned from Emmy Noether's life and work. When I was a graduate student in the United States, every graduate student had a list of our heroes in mathematics, except that in every list there was one woman who was Emmy Noether. And why was Emmy Noether so important for me as a woman doing a PhD in mathematics in a community that was really not that open towards women doing mathematics at PhD? And that's what I want to explain, and I want to explain through the words of Hermann Weyl in his memorial address. When I was called permanently to Göttingen, I earnestly tried to obtain from the ministerium a better position for Emmy Noether, because I was ashamed to occupy such a preferred position beside her, whom I knew to be my superior as a mathematician in many respects, and this is Hermann Weyl. I did not succeed, nor did any attempt to push her through her election as a member of the Göttingen Gesellschaft tradition. Excuse me. I'm like who wrote Huckleberry thing? Mark Twain. There's a quote of Mark Twain. I had to study German to get my PhD, and there was a quote of Mark Twain, sorry, that was on all of our walls. Life is too short to learn German. So we learned how to do it by, it was so difficult. It was much more difficult than number theory, believe me. So tradition, prejudice, external considerations weighted the balance against her scientific merits and scientific greatness, by that time denied by no one. So, what I learned from her was the untruth of several myths about the activity and the mathematical community at the time, and this is in Spanish because I really want every student here to understand it. So, first, the myth that mathematics is not an activity of women. Well, most of the men mathematicians that I know cannot really understand the work of Emmy Noether and do not reach. That does not mean that you have to be a great mathematician like Emmy Noether. I believe that you can be a very happy mathematician, having a very happy life as a woman, and just be a regular mathematician. So I'm not saying that you need to be a heroine like her. No, I'm saying that she taught me that what they were telling me was a lie. So I knew it was a lie. Second, only white male can do mathematics well. Okay. I was in the United States, so understand my context. Mathematicians work in complete isolation. If you're in Spain, you can only say, and they don't study. They are so smart, great mathematicians, that it comes by osmosis. Good students never study. There is such a good student in my class, he never needs to study. Well, you're so naive. It's a myth. Mathematics and politics never mix. It's a lie. It's a lie, and students need to learn it's a lie. Only 8% of students voted 2 days ago, to your shame. I was thinking of going on strike and not teaching for 3 weeks because I'm ashamed of the student community in this university. 8% of the students did vote. And that's a shame. Shame on you. Because you don't know that mathematics and politics are mixed all the time. Mathematics are a totally objective discipline. Well, then look the other way. You know how I am, Giovanni. Sorry, I had to take this opportunity. You give me the stage, I take it. You don't pay me for this work, so I may as well get some benefit, right? Look, mathematicians make their best work when they are young, and then to finish, I have we have the case of Einstein's and Weyl's words telling us how her best work was done in her late years, but I have a little research on how many mathematicians. This was started in that meeting in Lumini that I was telling you before, where Mariemi and me were. It was started with the organizer Eva Bayer from Lausanne. We started this research there because it came out this horrible book, Many Mathematics, with this other horrible book, Apology of a Mathematician by Hardy. They are both really despicable books, in my opinion, in this sense, that they really believe that mathematics are done by young, isolated, possibly sportive men. And the truth of the matter is that there are only 3 cases. They both, Bell and Hardy, give us examples because they are the only 2 existing ones. Abel died young, Galois died young, Riemann died young. So we don't know what they would have done if they had kept living. Now, here are some cases. When you're old, Galileo, Cavalieri, Descartes, Newton, their best work is done when they are old, certainly above 40 years, which is the Fields Medals research. Lagrange, what he did when he had 75. Gauss, Moebius, the Moebius ones, he was 68. What they keep doing in general, mathematicians start strong and they keep being strong all their lives. And it's not true. Here are just some of the examples that you have. And I check at those posters that you have, and in CV Math, you have, okay, and I'll jump this. I'm done.
Thank you very much, Capi.
You're very welcome, Giovanni.
Do you guys have any questions?
I'll translate it, that's okay.
No es tanto una pregunta, sino agradecerte que seas un ejemplo a seguir para todas las estudiantes que estamos aquí, porque demuestras que podemos ser matemáticas. Oh, perdona, que me estoy emocionando.
It's not a question, it's just that she's thanking me for being a role model for the students, female students, because I am proof that you can be. What can I do? ¿Qué es lo que soy, Gloria? Miedo me das, Gloria.
No, que podemos ser matemáticas y que podemos luchar por lo que realmente nos apasiona. Así que muchísimas gracias.
I'm a proof that we can be mathematicians and fight for what gives us passion. So, thank you, Gloria. Gracias a ti.
I have a comment because I think that through your talk we somehow got an answer to the mailing between Hasse and Frankel. So apparently through your to the questions you asked to the colleagues in the faculty, it turns out that the word liberated appeared in the way Emmy Noether liberated linear algebra from just being obscure formulas with determinants.
Yes.
So probably she would have been a very good teacher. She was a good teacher because she found the right way to present elementary facts like isomorphism theorems in a way that is more elegant and probably more effective, even for first or second year students. So maybe that is an answer. She might have been a good teacher. I don't know.
But then think of the students in this university. Which are the three subjects? I'm talking about subjects which are required. Required courses, everybody knows, not optative courses like commutative algebra whatsoever. The three required courses that are totally shaped in her language are linear algebra. And the students go, ugh!
Well, that's not true.
I'm talking of my students here, because when I use linear algebra in algebraic structures, in algebraic equations, in number theory, this linear algebra, they don't even know the teacher who taught them. Unless it's Gamboa, they never know the name of the teacher. But that's because Gamboa is quite a noticeable person in many levels. And a great teacher also, but he's noticeable. But linear algebra, algebraic structures, which is a very difficult course because it's the first time that they learn to use 20th century language. And then algebraic equations. And by the time they reach algebraic equations, they need to know algebraic structure and linear algebra. And because they haven't understood linear algebra or algebraic structures, they are lost in what I think is the most beautiful subject in the entire career. So if you probably ask them, I would say that they didn't really understand the depth and beauty of that language. And I think that Mariemi agrees with that. And
You're not heard at all.
But the point is, of course,
I didn't say that, he said it.
yeah. No, but as a matter of fact, her point of view was revolutionary. And it might well be that the colleagues would not have liked her to just change completely all kind of teaching. If I see how persistent traditions in teaching can be, changing this can really be perceived as threatening by other people. Right? So she had certainly very strong opinions about how to present material, and this would not have been a consensus at that time. And to show all the other guys, how you're doing algebra is fine, but now I will show you how to do it right, would have been probably difficult to accept.
Totally agree. I totally agree. Yeah. Thank you.
Okay, so if there is no other question, I would really like to thank both Ilka Agricola and Capi Corrales for this nice afternoon with Emmy Noether. I personally really liked it and I enjoyed it a lot, and I hope you did too. So thank again.
Thank you.